welcome to Mrs. Edwards' math class. My name is Casey Ellison. Please do your homework, and I hope to see you guys at the next football game. And please be on time for school next GL. Okay, peace out.
Thanks, bud. All right, everybody. Down to business here. Let's take a look at problem 4 from 2018. Once I get my tripod settled here. Hold on. Sorry, guys. Usually I do the adjustments before I start the video. Let's see what we can do here. Come on, tripod. All right. Okay, I think we got it. All right, my friends. Okay, 2018, a true test of reading comprehension. It says the height of a tree at time t is given by the twice differentiable function h, where h of t is measured in meters and t is measured in years. Selected values of h of t are given in the table above. I've mentioned this before, but if the problems where they give you tables give you grief, it really does simplify things to sketch out a little graph of the information. And the graph does not need to be award-winning. You can scribble on it as much as you want to, because it would be your own scratch work, and it wouldn't be the kind of thing that they would grade you on or dock you points for or anything. It's just your own scratch work, okay? So, and I'll use the picture to explain things here. So for part A, it says use the data in the table to estimate h prime of 6 using correct units. Interpret the meaning of h prime of 6 in the context of the problem. So here's the idea. There is some continuous function that connects these dots, and even though they didn't say continuous, differentiability implies continuity. So there's some continuous graph here that connects all these dots. We don't know exactly what it is, but I could kind of guess, and fill those things in. So they want to know what h prime of 6 is. Well, they didn't give us the function to take the derivative of and all that. So 6 is right between the 5 and the 7. So here's what they want. They want to know what the slope of the tangent line is at 6. But we're going to approximate it by doing the slope of the secant line with the data points that are on either side of that. So so here we go. So h prime of 6 would be approximately the height at 7 years, take away the height at 5, all over 7 minus 5. And then that would be, so h prime of 6 then in turn would be approximately h of 7 is 11, h of 5 is 6, over 7 minus 5 is 2. Units of measure, you're always going to want to add that in, even if they don't ask for it, but they did specifically ask for it. So 11 minus 6 what? That was meters. And then 7 minus 5 what? That was years. And so you could always do this little trick if you get stuck on what the units of measure are. So you're going to end up with something equivalent to 2.5 meters per year. There we go. Now they asked us to, using correct units, interpret the meaning in context of the problem. So, so our answer here, this means that the height of the tree when t equals 6 is increasing at a rate of approximately 2.5 meters per year. There we go. Okay, and that is it for part A. Moving on to part B, I did a little pre-writing for you just because this problem is kind of a long explanation in the first place. But for part B, they said, explain why there must be at least one time t between 2 and 10 such that the instantaneous rate is 2. I'm going to use the mean value theorem to explain, to argue this one. So just a quick review. If you know your function is continuous and differentiable on a given interval, then we're going to know that there exists at least one value, I'm going to call it c, between a and b, such that, and let me draw a picture and then we'll say like what the statement is that goes with it, okay? So here's the idea. You've got an interval from a to b, and you have, you know, f of a is something and f of b is something, and you have this function that's continuous and differentiable. That means it's smooth and continuous. Differentiable means no corners, no cusps. Continuous means no vertical asymptotes or discontinuities. And so the mean value theorem is where you basically know that since your function is continuous and differentiable on your interval, that if you found the average rate of change or the slope of the secant line, that that should equal your instantaneous rate or your derivative in at least one place. And in this picture, it happens in 2 places. So maybe I would call this C1 and then this one C2 or something like that, okay? So now how to say that in math speak. We would say there exists at least one value C, that would be these guys, such that f prime at that c value is equal to the same as the average rate of change. So that would be f of b minus f of a all over b minus a, like so, okay? So now with that said, I'm going to bring this picture back. And you can see I drew this picture quite a few times. If I was doing this on a test, I would have drawn it once and then just kind of erased and gone back to the same picture. I wouldn't have drawn it 3 times. But you know, you've got some smooth continuous function that connects the dots that represents the height of the tree. What I did was I just did slopes of lines on each interval, looking for one interval where the slope of the line of the secant line would be 2. And I found that on the interval from 3 to 5, if you do the slope formula, you end up, you know, the slope there is 6 minus 2 or 4 over 5 minus 3 or 2. So the slope of that secant line is 2. And in the original write-up, they said that H is twice differentiable, and differentiability implies continuity. So, so what that means is there's at least one place between 3 and 5 such that the slope of the tangent line would also be 2. So now it's just a matter of writing that down. To write that down, I would say, since H is continuous and differentiable, and again, they did not specifically say that it was continuous, but differentiability, you can't have differentiability without continuity, so differentiability implies continuity. On the interval from 3 to 5, and h of 5 minus h of 3 over 5 minus 3 ends up being 2. The mean value theorem guarantees that there exists at least one value, I'll call it C, that lives somewhere between 3 and 5, such that f prime of C would equal that 2. There you go. Okay. You wouldn't have to say the mean value theorem guarantees, but by mentioning the mean value theorem, it makes whoever's grading your test, makes it easier for them to just look at your work and be like, oh yeah, full credit. You know, they're using the correct theory. But if you were to say, you know, a lot of this without specifically saying that, you'd be fine as well. Okay, and I think that's all we needed to do for part B. So let's move on to part C. Okay. Part C says use the trapezoidal sum with the four subintervals indicated by the data in the table to approximate the average height of the tree over the time interval from 2 to 10. So here's the picture again. And so let's get clear on what they're asking us for. So first of all, they want us to approximate the average height of the tree over this interval from 2 to 10 there. So let's think about how do you find the average value of a function? And there's average value and there's average rate. So make sure that you can be clear on which one's which, okay? So we're finding the average height of the tree, and then AKA, the average value of h of t on the interval from 2 to 10. And that would equal, so how do you find the average value? You add up all the values, and so that would be the integral from 2 to 10 of h of t dt, and then you divide by the number of values, which would be 10 minus 2. I'm going to write this a little simpler. I'm going to write it as, instead of dividing by 8, as 1/8 times the integral from 2 to 10 of h of t dt. Okay, now let's talk about approximating this the way that they want you to. Remember that there is, you know, some twice differentiable function that, you know, connects all these points here, but we'll never know exactly what it is. But they're saying use a trapezoidal sum with 4 subintervals indicated by the data. So to approximate this interval. So what we're going to do is we're going to do one trapezoid that goes from 2 to 3, and it's a trapezoid, so it'll be straight at the top here. Another trapezoid that goes from 3 to 5, and then it would be straight here. 5 to 7, straight at the top. And then 7 to 10, and it would be straight at the top there, okay? And it, of course, wouldn't be the exact value as the real area, but it's probably a pretty good approximation. So I'm going to change my symbol to approximately equal to. I'm going to bring the 1/8 down, and then we are going to approximate this integral using areas of trapezoids. So a quick review, just a quick geometry review. If you have a trapezoid, so like let's say these are the bases, and then this would be the height. The area of a trapezoid, the way you find it, is you do the average of the bases, so that means you add them up and you divide by 2, and then you could multiply by the height. Anything equivalent to that does the trick. So let's approximate this interval. So first let's do the part that goes from 2 to 3.
Mama, where's the workman?
They left. They'll come back on Monday or Tuesday. All right. Sorry, you guys. So let's see. Base 1 would be 1.5. Base 2 would be 2. Divide it by 2 to average it, and then multiply it by the height, which would be from 2 to 3, which is 1. Trapezoid number 2 here. We'd have base 1 plus base 2 divided by 2 times the height, 3 to 5 would be 2 units. Okay, trapezoid number 3 would be 6 plus 11 over 2 times 2. And then trapezoid number 4 here would be 11 plus 15 over 2 times the height here is 7 to 10, which is 3. Oh, a comment. We had learned something earlier in the year called the trapezoidal rule. The trapezoidal rule is for when the subintervals are all evenly spaced. They're all of the same size. So we wouldn't use the trapezoidal rule for this. We would just go back to old school geometry like we are here. Okay. Now, this was a non-calculator problem. On your test, you won't have any non-calculator problems. But I always used to say with the non-calculator problems, you're always welcome to stop and just say meters on an answer, and they would have to accept your pre-simplified answer. But if you cannot bring yourself to leave an answer so unsimplified, then you could always, simplify it something like this. So 1.5 plus 2 is 3.5, divided by 2 is 1 3/4. Here the 2's cancel, so you'd be left with 8. Here the 2's cancel, you'd be left with 17. Here, 11 plus 15 is 26, divided by 2 is 13. 13 times 3 is 39. Adding all this stuff up, you would end up with 1 plus 8 plus 17 plus 39 is 65. So you'd have 65 3/4. And then you could always think of this as let's see, sorry, 65 3/4 over 8. And again, you can always just stop at any time and just say meters and be like, boom, I'm done. But you could stop and say meters here, but to clear the fraction, if you're a purist, you could always clear the fraction out, multiply by 4 over 4, you'd end up sooner or later with 263 over 32 meters. There we go, and that would be your average height of the tree. Notice the way I wrote it. I have the prompt here, and then it's, equal to this, and then I turned it into an approximation. So it's implied that the average height would be approximately to this. So if you didn't want to rewrite it, you wouldn't have to. Okay, that's part C. Now let's move on to part D. I love part D because I have a sick love for related rate problems. Anyway, so part D is actually a related rate problem worded in a way that makes you maybe not realize that that's what it was. But anyway, it says the height of the tree in meters can also be modeled by the function g, given by g of x equals 100x divided by the quantity 1 plus x, where x is the diameter of the base of the tree in meters. I'm going to stop right there and just kind of draw a picture of what's happening here. So let's say this is your tree. G of x is the height, and it's a function of x, so it's the height of the tree in meters, right? Yeah. So the idea is that if you know the diameter of the tree at the bottom, you could plug it into this rule and it would give you the height of the tree. That's kind of fun. Anyway, so for this problem, I really like the idea of a have-want structure. So this is something that we'd have. They also told us that when the tree is 50 meters tall, the diameter of the base of the tree is increasing at a rate of 0.03 meters per year. So that means that we would know that the change in the diameter with respect to time at the moment when the height is 50 would be equal to 0.03 meters per year. Okay? So this would be stuff that we have. So now what is it that we want? We want the rate of change of the height of the tree, so change in height of the tree with respect to time, at the time when the tree is 50 meters tall. Okay, so this is just me putting what we have and what we want into math speak, okay? So now let's think about, one thing I'll do is I'm going to change, I personally like it a little better when this just says g equals 100x over 1 plus x. It's just a style thing. So I'm going to go ahead and rewrite it like that. And then what do I need to do 2g to get dg dt? Well, I need to take the derivative with respect to t. So I'm going to go ahead and write that. Like so. And then the left side's easy. It's just dg dt. And then the right side, keep in mind you're taking the derivative with respect to time of something that's in terms of x. And x is this diameter of the tree, and as time changes, so does x. So x is a hidden function of time. So let's diagnose this situation. We're gonna need to use quotient rule, and within quotient rule, we're gonna need to use chain rule since x is a function of time. So let's do it. Low d high would be 100 times dx dt. There's a little chain rule there for you. Plus high, d low, all over the bottom squared we go. Okay, so now for dg dt at the moment when g is 50. So if we're figuring this out at the moment when g is 50, we're going to need to figure out what is x when g is 50. So I'll do that kind of over here. So x when g is 50. To find that, I would just go here and then put 50 here and then just solve for x. So okay, now if you can solve this by inspection and you can just see x equals 1 makes this work, then good for you. If you can't, then you just do a little algebra. So multiply both sides by 1 plus x. Subtract the 50 over. And then there you can really see that x equals 1 would be the solution here. So x when g is 50 is 1. So that means that since we're finding what this would be when at the moment when g is 50, we'll just be able to put 1s in for all of the x's. And then what are we going to put in for dx dt? Well, since we're doing this when g is 50, and they said dx dt when g is 50 is 0.03, we're going to be able to put 0.03 in for those. So we'll end up with 1 plus 1 times 100 times 0.03 plus 100 times 1 times 0.03 all over 1 plus 1 squared. So what's that? Okay, so we've got 2 times 3, which I would say is 6, plus 100 times 3 100ths, which is 3 over 4. Whoops. No, minus. Low D high minus high D low. Oh no. Oh no. All right, if you guys were here watching me, I know you would have called me out on that a while back. Okay. All right, minus high D low. Okay, there we go. Okay, so 6 minus 3 is 3, so we were left with 3/4. All right, and then 3/4 what? We were finding the rate of change of the height of the tree with respect to time at this moment. And so that would be 3/4 meters per year. All right, there we go, my friends. I hope this helps, and I hope everybody's doing great. Take care, everybody.